flip back over here. Guys, all right so far? Right, so again, focus on special relativity, but hold on to the idea of general relativity because I'll come back eventually. Okay. And let's take a look at this page that you guys picked up from the right side of your desk. Okay. So I want to take you guys through these special relativity equations, and might still have one of these by the end of today. Okay, so here, look, the first one, we got a time dilation. So, okay, so this would be like Earth twins time compared to rocket twins time, right? Just divide by this Lorentz factor, that's the relationship. Now, there's some other dilations that have to go hand in hand with that, and that's the next couple of these things. Let me explain this length dilation, because that looks pretty similar too. Looks like rocket twins length multiplied by this Lorentz factor. What's all that about? Well, think about it like this. For this to all be consistent, you might have something like here. Here's our sun, maybe our planets. So here's our solar system. Here's like Jupiter and Saturn and right, the whole deal. Okay. Okay. So here's our solar system. Let's say way off in the distance is like some other solar system. So here's like some other solar system here. Right? It's got its own planets and its own thing going on. And let's say you want to travel from here to here. And I'm just going to make up something crazy. Let's say this is like 10 light years, just to make up something. Say 10 light years. Okay. So we send off someone at, let's say a rocket at like half the speed of light, half the speed of light. Well, relative to us on Earth, shouldn't it take like 20 years to cross 10 light years? Because so light, it would take 10 years to travel half the speed of light, should take 20 years, right? But you guys know special relativity, you guys remember the twin paradox. So what looks like 20 years to us, just stationary, to someone aboard this rocket ship, it's not going to take 20 years. Maybe it only takes 5, 10, 15 years from their reference frame. How do you cross 10 light years in smaller than 10 years? Because there's that time dilation. But the only thing to make that consistent is that there must be a length contraction. So if you're on the ship, this doesn't look like 10 light years of distance anymore. It actually looks like a shorter distance. And that distance is take the original distance and multiply it by this Lorentz contraction factor, like that. There's also, guys got that? So there's a time dilation. There must also be a length dilation. There's also this mass dilation. So if you take the rest mass divided by the Lorentz factor, and you know where particle physicists see this all the time over at the Large Hadron Collider at CERN, because say they put in like, just make up some numbers, let's say 1 gram of material, and there's this huge synchrotron that runs under the border of Switzerland and France. They get these particles moving up to like almost the speed of light, it's like 99.9 something percent speed of light. What they notice is that the mass appears to dilate. So if they've only put in 1 gram of material, it might dilate to like 100 grams of material. Where'd all that extra mass come from? Well, it's this relativistic effect. Now, from this one, you can also show mass energy equivalence. That's what this last one is, E equals mc squared. E equals mc squared is the equation of nuclear reactions. When you guys took chemistry, you guys learned that mass is conserved, conservation of mass. So for every gram of reactants you have, you're going to get 1 gram of products. Right? Mass has to equate before and after a chemical reaction. Now, nuclear reaction, that's not exactly true. If you run a nuclear reaction, fission, fusion, talk about those, there's going to be a different amount of mass after the fact. Well, less if you're getting energy out of the system. But you can account for it with this equation, and it's an enormous amount of energy. E is energy in this mass. So if you take the mass difference, right, you're saying, well, where'd all this missing mass go? Multiply by the speed of light squared. Now, speed of light itself is already a huge number. It's like 10 to the 8. Square that out on another 8 zeros, right? Multiply that by the missing mass, and now that's the energy of nuclear power plants, atomic bombs, anything where you're running a nuclear reaction and getting energy out of that. Right, so quick glance at the problems here. The first 3 are Earth twin and rocket twin, twin paradox scenarios for time dilation, length dilation, and mass dilation. We got some mass energy equivalence questions, some conceptual questions. So you guys can do some limit questions, and yeah. So we'll save some of these for tomorrow. Okay, you guys got any questions today?